All right, I'll begin with a word of prayer. Heavenly Father, we thank you for this time we have to meet together and study your creation. We just pray that we'd use this time wisely, that we'd understand more about differential forms and pullbacks and all this, and that you'd just be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. So my point last time is essentially that if you really boil it down, the pullback is, in some sense, just a way of, systematizing a substitution for differential forms. It's something like that. And so like here's an example. So this whole section 10.7.1 is the intuitive computation of pullbacks. And like I was telling you, I hope we can understand the implicit function theorem in retrospect in this notation, come to some sort of calculational principle, some sort of understanding of what the existence of a differential form of a particular type on our space means. Yeah, that's a larger goal. So here, just for specific context here, I'm going to look at f of uv equal to xyz, okay? So that would make f a mapping from, let's say, ruv to rxyz, all right? And so we can calculate df pushing forward partial u, and we'll get x, well, let's say partial x, fine, xu partial x plus, yu partial z plus the partial derivative of z with respect to u partial z. Let me write them. Golly, I'm not happy with that. I mean, it's not wrong, but it's just not right. So we have partial x, partial u, partial x, partial y, partial u, partial y, plus partial z, partial u, partial z. Likewise, if we look at the push forward of the v coordinate map, we get partial x, partial v, partial x, partial y, partial v, partial y, partial z, partial v, partial z. These are the push forwards of the coordinate derivations on our domain. So if we look at the pullback of a whoa? Oh yeah. Well, hold on a second here. Now, okay, so then if we look at an arbitrary one form, right, omega equals to adx plus bdy plus cdz, right? This would be a one form on R3, right? Then what's its pullback look like? We have, how's it go? So it's like f pullback omega on partial u du, right? Plus f pullback omega on partial v dv. That's essentially the definition. Well, that's not the definition of pullback yet. That's just the fact that any one form on our, my bad, these are missing a dimension, yeah? 2, 3, okay, yeah. So this is just the fact any one form on R2 where we're using u and v coordinates can be written as a du times a coefficient and a dv times a coefficient, where the coefficients are given by evaluation of the differential form on the coordinate partials, right? That's how we select the components of a one form. And then by definition, this is, df Oh, I'm so sorry. I've lost my way. So that's omega of df acting on partial u, I believe, right? Yeah. Omega acting on df of partial v. That right there is the definition of the push forward. You push the vector forward, you let it act on then you let the differential form in the range act on the push forward of the vector from the domain, right? Because df partial u is, after all, right, these are both in the tangent space, to R3, right? If you fix a point, they're to be more honest, these are really, elements of the vector fields on R3, right? They're vector fields on R3 if we allow the point to vary. But anyway, so this is that up there, right? And but of course the omega is what? The omega is ADX right here, right? So what happens when that hits these, right? You've got ADX plus BDY plus CDZ acting on, I'm gonna drop to the easier notation. That. And of course I've lost my, what I lose? I lost my du, my dv. And so what happens with all this? Well, so, in short, this only is non-trivial on that, right? And this is only non-trivial on that. This is only non-trivial on that. And so we end up with just A partial x partial u plus B partial y partial u plus C partial z partial u du, right? Plus A partial x partial v plus B partial y partial v plus C partial z partial v dv. Which we can rewrite as A times partial x partial u du plus partial y partial v dv, right? Plus B times partial y partial u du plus partial y partial v dv plus C times partial z partial u du plus partial z partial v dv, right? Which is literally what? ADX plus BDY plus C dz, where we've got x is equal to x of uv, y is equal to y of uv, and z is equal to z of uv, right? So as a matter of practical computation, we can just plug in the formulas and take total differentials and like work it out. Let's see, let's try to put this into practice for a specific function. Let's see here, like if we had f of, let's say, uv equal to, oh, I don't know, u squared plus v squared uv and 3, right? Then, you know, if I have a differential form like omega, you know, let's say x dy plus y dz, for instance. That's a differential form on R3. What's its pullback under F? So I just look, I go, okay, this is my x, this is my y, this is my z, right? So I've got u squared plus v squared, differential of uv, right? Plus uv times the differential of 3. So in this case, I would just get, you know, u squared plus v squared times v du plus u dv. And that would be the pullback of that one form under this map. Let's see here. On the other hand, we call that omega 1. All right. If I had omega 2 is equal to, like, you know, x plus y dz, right? Then it's pretty clear that the pullback of omega 2 is what? Right. But ultimately, the dz, 0. Let's see here. If we like pull back, you know, x dx, we get what? We get u squared plus v squared times 2u du plus 2v dv, right? All right. So I warned you, I was going to endeavor to understand the implicit function theorem as it's stated in differential forms. Now there's two advanced calculus books by Edwards. They're very, very different Edwards. So there's C.H. Edwards, who wrote that Dover book that I like from the start of the course, all right? Which does have a whole chapter on integration of forms. It has a full-on proof of generalized Stokes theorem for Rn. It's a pretty detailed proof. It takes up tens of pages in that book, if I remember right. It's lengthy. But then there is a different Edwards, who I don't remember the... Just a second, I'll tell you. It's a green book. I don't think I've ever shown it to you. But this is from H.M. Edwards, Advanced Calculus and Differential Forms Approach. And H.M. Edwards, Advanced Calculus, a Differential Forms Approach, is a curious book. It's very much written in the style of 19th century calculus, 19th century mathematics. And by that I mean that the role of functions is not emphasized. Rather, It's equations. It's centered, the discussion, the theorems, the thought, everything is around equations, not functions. That's not the case for C.H. Edwards. Like the Dover book, that is definitely a book that embraces the concept of function and domain and uses them meaningfully for the most part throughout the presentation. Edwards' differential forms approach is much more of a 19th century, a proof would maybe just be given in terms of an equation or something. And it's unsettling for me as I've grown up in the world of function thinking, and sometimes I have a hard time understanding what he's meaning by something. But nevertheless, it is an endless source of really cool ideas and calculations and stuff. It's a fun book to read. And one of the things in there that I only partly understand is his characterization of the implicit function theorem in view of differential forms. So let's just, this is pretty low-hanging fruit. Let's just try to understand example 1 as it relates to the implicit function theorem if we can. Like, what would the implicit function theorem even look like here? What could you do with example, we've got, f of uv equal to u squared plus v squared, uv, and 3. I mean, does it even make sense to talk about the implicit function theorem here? I'm not entirely sure. I got to put on my thinking hat. Like, how would we... Usually when I think about implicit function theorem, I do what? I think about an equation or a set of equations defining something, So if I was to think about... See, I don't even know where to start in terms of implicit function theorem here. I guess the deeper question I'm trying to ask here is, what is the geometry of this map? What can we see about the geometry of the map from the pullback? And I think at the present stage, my most natural understanding of it is that we could view this as a parameterization from like from R2, right? With UV coordinates to, R3, X, Y, Z, right? And this particular thing, like the image, right? F of R UV is actually, equal to what? Something like, well, it's a subset of a plane, right? It's all inside the what? This is the z equals 3 plane, right? And so I guess what I'm seeing is that the differential forms over here pull back. Let me put it in a sentence. Differential forms and on, let's say, P, pull back to non-trivial forms in R2 UV. Now, what do I mean by differential forms on P, though? So here I'm working off raw intuition, which is just that, obviously on P, what do you have? You have z equals to 3, so dz equals to 0 here, right? So like an arbitrary, a non-trivial one form at least on dz is what? So like basically we're looking at alpha is equal, or omega rather, omega equal to something like, you know, a dx plus b dy. That's what a non-trivial one form looks like on the, you know, the plane there. And those are the ones, of course, like omega 1 and omega 2 and well, not omega 2. Omega 2 would not be. Omega 2 is trivial. dz is equal to 0 when we look at just the plane itself. All right. Now, let's see here, what else can I say? There's only really one interesting 2 form on the plane, right? So like, what's the only, there's the 2 form is something like, you know, some coefficient times dx wedge dy, right? And if we pull that thing back under, you know, that, well, then we would have a, and we have basically a, we plug in, you know, u squared plus v squared, uv, and 3 into the formula for a, right? And then dx is what? Well, dx is 2u du plus 2v dv, right? And you take that, your dx, and you wedge that with dy, which is what? Your v du plus u dv, right? And that gives us what? My a evaluated at that point, right? Times what? Well, I get 2u squared minus 2v squared, I think, du wedge dv. Because u squared, v squared, but I have to flippy-flop them to get it in that order. The u wedge u and the v wedge v are 0. So there you go. That's probably non-zero. Well, that's got trouble though, doesn't it? Right? I mean, that is a at the point, right? So it's 2a at the point. Then you got u plus v times u minus v du wedge dv, right? This suggests to me that something funny happens with the parameterization along the u equals to plus or minus v parameter lines. If we're looking at this as a parameterization of the plane, admittedly a weird parameterization of the plane, but a parameterization nonetheless. Can you see, let's see here. So thinking Calc 3 for a second. This is like, you know, big X of uv or r in the Calc 3 notation, right? And to calculate the normal, remember what we do? We do like partial x, partial u, Cartesian cross product, partial x, partial v, right? That gives me the normal to the surface. And so here, that would be, you know, 2u v 0 cross product with 2v u 0. And that is, what is that? That's 0. Let's see here. 0. Oh, well, yeah. That's not an accident. So you notice that the normal to the surface defined by this map, right, is equal to 0 when u is equal to plus or minus v. It is no accident that the 2 form, right, that's available on the surface, namely adx plus b, the only 2 form that's available on the surface is dx wedge dy, right? So that pulls back to 0 in the case that, exactly the same case that the normal vector field is degenerate 0, right? We would say that the surface isn't regular in the language of Calc 3 at that point, right? So somehow the pullback is getting at some of the same data. Now there's something I did here that's all kind of a little bit annoying, right? Which is that I'm flip-flopping back and forth between the parametric versus the implicit viewpoint, in the sense that I took a sort of implicit viewpoint in order to see that z equals to 3 is the surface, so dz is equal to 0, and yet, yeah. Let's see here. So let me try something. Yowzers. I need to think about a good implicit function example that we can kind of tear into for a second. Like, let's see here. Example 3. Something like g of, how's it go? T, x, y, z equal to, all right, so let's see here, something like t squared plus x squared, and then y squared plus z squared. So what is this place? Sometimes I honestly don't know, Ernesto. Like the girls, they're just goofy. I think it's because we're too close to. Okay, I will not document my aversion to other majors. I'll try to behave. So like here, G would be a mapping. G would be a mapping from what? From like R4, which I'm apparently using T, X, Y, Z coordinates, to R2, which let's suppose I'll use UV coordinates for, okay? And of course, we could define a level surface in R4. How would we do it? For example, we could look at like G of, T, X, Y, Z equal to, like 1, 4 or something, right? That would give us a particular subset of R3. Now, I probably should do something like, this is too nice. I think we won't be able to see. All right, you know what? We're just going to stick with it. It might be too nice, but let's just. Nope. I'm going to do. I can't make up my mind. I'll leave it. All right, so here, we only have if we're going to look at the pullback under G, right? Does that make sense? I mean, we can. What's the top form here? So I've got, we've got U is t squared plus x squared. I've got V is y squared plus z squared, right? And so I can pull back du wedge dv, see what happens there, right? Oh, okay. I was afraid I'd wasted more time. It's just my mind spinning, it's not my marker. All right, so pull back. G pull back. du wedge dv, what's that give us? Hey, good, you're home. That gives us, well, you know how, I mean, let's get to the point. It gives us this. Right? I mean, that's what happens because u is equal to x squared plus a t squared plus x squared, and the v is y squared plus z squared. So we get, what do we get? Well, we get 2t dt plus 2x dx wedged with 2y dy plus 2z dz, which gives us what? See, what I really should do here, if I was teaching this course better, Ernesto, I would already have in my hand a half dozen examples from earlier in the course with different implicit function examples where I have different dimensions laid out with trouble spots, and then we can go back to that set of examples and like hit it with the differential forms technique and understand how the differential forms are uncovering the same data. Unfortunately, I haven't taken that much time, my bad, but you know, maybe some year. So sorry, 4, and we got what? We've got, you know, 4 ty dt wedge dy plus, I'm just factored the 4 out, and then you got your tz dt wedge dz, right? And then you got yourself, what? xy dx wedge dy plus xz dx wedge dz. So just to picture it, we're pulling back, right? We've got this du wedge dv over here, right? And we're pulling it back. We're pulling that thing back. Let me call this thing gamma. And this is g, right? Whatever your favorite picture for R4 is, right? And over here, you're looking at the pullback of g. A pullback of gamma over here, right? of course, the thing is, here we've got, we're talking about it. We're talking about this 2 form at the point u naught v naught, right? Where this point over here, let's say p naught, we have g of p naught equal to u naught v naught, right? That's the game. We're pulling it back to that point. So maybe we can understand something about so like the pullback of that the pullback of the plane, right? It's some kind of, I don't know what the right picture is, but it's some kind of surface in R4, right? I don't know what that looks like, but some kind of surface, right? This right here is it's really the pullback of R2 itself, right? I mean, I'm saying really I'm saying G inverse of R2, right? The set inside the R4 that maps to that. So if I take a particular point in here, right? Then the question is, at that point P naught, right? Here's the question. Can I use T, X, Y, Z as coordinates? Let me call this thing S for S. So, of course, I don't use all 4 of them. S is a 2-dimensional thing. So the real question is, like, can I use T and X? Could I use T and Y? Could I use T and Z? Could I use X and Y? Could I use X and Z? Could I use, X, oh, I already did that. TX, TY, TZ, XY, XZ, YZ. Those are the distinct pairs to choose from 4, right? 4 choose 2 is 6 possibilities. So the answer to whether or not it's possible to use the coordinates as portrayed there at the point P naught is tantamount to the question of how the coefficient up in here behaves. So like, for instance, Tx, all right? The answer is no. I can't. There is no dt wedge dx here. And also, what else can I do? Can I not do ty and tz are okay, x and y are okay, x and z are okay, but y and z, not allowed. And you can kind of see why that is, because just using t and x and using y and z as coordinates, it doesn't somehow reflect the fact that these are isolated in the formulas, but that doesn't quite explain it. The real question is, like, what are these things here? So on the other hand, xy. This one here, yes, so look at xy, dx wedge dy. If xy is not equal to 0 at the point. See, because if xy is equal to 0, then this part of the 2 form is vanishing. So why am I claiming that? Well, I'm using the implicit function theorem, actually. Do you remember the implicit function theorem? The implicit function theorem, for example, said that I could solve, for instance, let's talk about x and y. I could solve for x and y if what? If I took partial xy, partial uv, right? No, other way around. If I took partial u, partial uv, partial xy, and that was a invertible 2x2 matrix, if I remember right. Is that right? I don't have those notes on me. Well, let's see here. So what this meant what? This meant, this particularly was the matrix. This was the matrix ux, vx, uy, vy, right? Which for our current example, my ux is 2x, my vx is 0, my uy is 0, my vy is 2y, and the determinant of this is 4xy. Not an accident. Now, in the notes in this section, I use, so you know, there's two schools of thought, and so like in the notes, I'm using the partial. I'm using this to be equal to that. So these are actually determinants. So this notation is at odds with the notation we used earlier from Edwards, C.H. Edwards, was that this is just a matrix, if I remember right. So just be warned that sometimes this is meant to be a matrix by some folks, other folks mean it to be the determinant of that matrix. This is just the confusion also that's implicit in like calculus 3, where we either talk about the Jacobian or the Jacobian, which usually means the matrix of the Jacobian determinant. Excuse me, it means the determinant of the Jacobian matrix. So just beware, context should guide you. But in short, if I adopt the notation of H.M. Edwards, then these coefficients, like every one of these, if I was to rewrite this, I could tell you this, like the G pullback du wedge dv is just literally partial, you know, uv partial xy dx wedge dy plus like partial uv partial xz dx wedge dz plus so forth and so on. Like there's 6 possible mixed determinant partials, and that's exactly what the pullback does, is it calculates the determinant of the submatrices of the total Jacobian matrix. Which is not an accident. Like the differential, the wedge product will give you access to like the Laplace expansion by minors for the determinant, and that's what's happening here at some level in the algebra. But so how to put this into words? How to put the implicit function theorem into words? Well, let me show you the words that H.M. Edwards gives us on this, and maybe I've done enough. Maybe I've done enough today for it to make sense. I'm not thoroughly convinced, but maybe. So So here's on page 247 of my notes. So we consider for I equals to 1, 2, da 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 m, y sub I equals to f sub I of x1 through xn. All right, where the f sub I are continuously differentiable near point, and we use bars. So this, the bars here are not like a different coordinate system, they're just a fixed point, okay? So I usually use a sub naught for a fixed point, but I believe I'm following the notation, again, of H.M. Edwards, so bear with me. Zooming in a bit, because it's a lot here. All right, so furthermore, denote the image of the fixed point by y bars. All right, so y bar I is equal to f I of x bar 1 dot x bar n. Again, for I equals 1 to m. All right. Suppose the following conditions are satisfied. Let me switch colors here. Beep, 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 beep. All right, so suppose the following. Actually, let me just get a better black marker. All right, so number one, using the determinant notation, all right? Number one, partial y1, yr, partial y1 through yr with respect to x1 through xr are not equal to 0 at x bar 1, x bar n. All right. And number two, the pullback of every k form k greater than r, all right, is identically 0 near the point. See here.